Okay, yeah, welcome back. Welcome to the second part of my course on optimal control and recent methods for solving optimal control problems. I was asked to put up the slide with the two QR codes. This is with the two QR codes. So the left one is for the for getting the slides. There's some feedback going on. Yeah, maybe lower, just lower. Yeah, and the second one is for the Moodle course for the course. So if you want to check out that, and this will also be. So if you download the slides via this QR code, you will also be able to. Yeah. Okay, 1, 2, 1, 2. It's still quite some echo. Check.
Info the Zoom. No, here, but this. Okay. Okay.
Because I logged in again. I'm not. Now it's again. Wait.
No.
Thank you. Okay, now I have to jump to where we stopped yesterday. Okay, there we are. Okay, yeah, so this is the optimal control problem we were considering, and I was about to explain, or I had explained, the Euler-Lagrange equations, which is a way to compute one single optimal trajectory, right? So we have an initial value fixed. We want to compute one optimal trajectory. We want to compute this control U. And the simplified setting here is that there are no constraints except for the ordinary differential equation itself, and that we look at controls which are continuous functions. And the conditions then are known as first order necessary conditions. So the conditions that we need. So if we have an optimal control U star, then there exists a function lambda star, this so-called adjoint or dual variable or co-state, which satisfies another differential equation. And this is a differential equation that determines how the system behaves. This is the co-state differential equation, and then there is a condition which effectively defines U star, and this has to be seen to be hold for all t, right? So it's really a condition for all t. We already did that. This is the compact way of writing that using the Hamiltonian, much more accessible, I think. So you define the Hamiltonian, this function up there, and then you can write that the differential equations, and also this additional condition, which is essentially a stationarity condition, is just via the Hamiltonian. Okay. Yeah. So let me start with a little example to write that down, which also shows what you can do with that. So this is a very simple problem. So we have the task to control the system from state 1 to state 0, like that car I had before. It's just even more simple dynamics, one-dimensional. So x dot is equal to u minus x. And we want to do so by minimizing this quadratic control term, the integral over that. So in a way, we would like to go from 1 to 0 with minimal control effort. That's how you can think about that. And if you write down the Hamiltonian, which is 1/2 the integrand, which is the integrand here, plus lambda times this right-hand side, the f here, u minus x, you easily can derive all these equations. What you see is that here, this takes a particular simple form. You can easily write u star in terms of lambda. The lambda equation is also very simple. You can solve that explicitly. It's just exponential of t times the initial condition. And then you can actually, and this is a task I will leave to you in case you are interested, you can actually just with pencil and paper compute the optimal control from these equations. That's not really difficult, right? So you can really do it. What you have to find is you have to find the initial condition lambda star of 0 such that this terminal condition is in the end satisfied. That's the only thing that has to be done. But if you write that down, you see immediately how that would look. I'm not doing that here, but just stating that this is really a tool which is not only potentially useful for numerical computations, but actually something you can, at least for simple problems, use to get just analytic expressions for the optimal control. So really write down a function, a term for a function depending on t. Okay, yeah, this was all in continuous time. Is there a discrete time counterpart to the Euler-Lagrange equations? Yes, the answer is there is. How do we do that? Well, effectively, if you look at this problem, this is just a nonlinear optimization problem written in a very particular form, like a finite dimensional nonlinear optimization problem where we have capital N vector valued decision variables, u of 0, u of 1, u of 2, and so on. And this is what we need to determine, right? So it's actually something that you can write down, solve with the usual technique for constraint optimization problems. You put this here as the condition that you couple with the Lagrange multiplier. So you define this Lagrangian. The only trick that you have to do is you define this pointwise in time. So of course, this should hold for any time t, but you write this like independently. And then you sum up the whole thing here, plus the violation of the initial condition should also be penalized. And then the usual stationarity conditions that you may know from nonlinear optimization will give you these kind of conditions here. And these are just the discrete time Euler-Lagrange equations. And they really have very similar structure. This is, again, the same conditions in a nutshell. If you write them down for the continuous time with the Hamiltonian, well, then the similarity is not so obvious. But if we write it down as we had it in the first version without the Hamiltonian, then you see it's really the same, right? So you have the differential equation for the state. Here you have the difference equation for the state. You have the differential equation for the co-state. Here you have a difference equation for the co-state. And you have the stationarity condition, which also looks very similar, right? And here this has to hold for all t. This also has to hold for all t except for the first one. So it's really a very similar structure. The only thing is that in discrete time, it's not really easy to define a meaningful Hamiltonian. So this is something that we lose in discrete time, but otherwise it's a very parallel structure in continuous and discrete time. Okay, yeah, that's all very nice, but as we already remarked yesterday, there are no input constraints, no state constraints, and for most practical problems, you would have them, right? So it's really hard to find a practical problem where you do not have constraints of any form. And this is the big contribution by the group of Kontriagin working in the USSR in the 1950s, that they were able to generalize the Euler-Lagrange equation to a similar kind of similar set of equations, but now involving also input and state constraints. Okay, yeah, so what we do now is we return to measurable controls and we add constraints. And let me start with input constraints and develop everything with just input constraints, so only constraints on u. And then later on, I will explain, or at least briefly tell you what happens if we have state constraints too. Yeah, so just for a change, I'm looking here at problems with free end time, right? So TF is an optimization variable over which we optimize, and we have a terminal constraint, meaning that we have here the requirement that at time TF we end up at x1. I will tell you about how things look if we do different things later on. But this is the setting for which I would like to develop the Kontriagin minimum principle. And the idea is that we first reformulate everything in this so-called Meyer form. I explained already yesterday how we do this. We define a new state C, which we define to be the integral over L. So this is now effectively the term that we want to minimize. We add this state C as an additional state to the state vector, get a new state vector x tilde here. Then we get a new differential equation where we have this L as the first component, and the initial condition, because we don't have a constant in front here, would be 0 for the first time and just x naught for the last. Right? And then we rewrite everything in this Meyer form here. We minimize now C of TF, and the conditions that we want to satisfy are now the conditions of this of this extended state, right, with this extended dynamics here. Yeah, then of course the Hamiltonian also gets lifted, so we can write it in that form, but actually it's more convenient to write it than in that form. Then you see what the difference is. The difference to the Hamiltonian I defined before is precisely this term lambda 0 of t, which appears because we have now turned the stage cost or the running cost into an additional state, an additional component of the vector field F. That's why it appears there. And then the theorem says, again, suppose that we have an optimal solution. In this setting now, the optimal solution consists of the control and of the optimal final time. And let x tilde star be the corresponding extended solution. Then again, there exists a multiplier which now consists of the original multiplier and this lambda 0 multiplier. We have these are exactly the first two equations of the Euler-Lagrange. So far nothing has really changed, but what changes is now that here we say that the function h attains its minimum on u at this point u star of t for almost all t, which means that the Hamiltonian, so before we had this condition that the Hamiltonian with respect to u, the derivative of the Hamiltonian with respect to u is 0. Now the condition is that the Hamiltonian is minimized, and by this I really mean globally minimized. And if I go back one slide, I have something which I didn't really mention so far. What we actually get is indeed a global minimizer there. So this is a big advantage, but of course we also, to get that, we also have to find a global minimizer of h pointwise in t. Okay, yeah. What else do we know? Well, interestingly enough, this lambda 0, this additional multiplier, can actually be shown to be constant. So it will not, it formally depends on time, but in practice it doesn't. So it's really a constant function. And also, as before, the Hamiltonian is as a function in t, evaluated along the optimal solution, is also a constant function. And if, as we said here, the final time is free, we get some so-called transversality condition, a condition at the end, which is this one here, that the Hamiltonian vanishes at the final time. And since it vanishes at the final time, it is constant, it must actually be 0 all the time. That's a consequence. I'm not going to talk about the proof. I first saw the proof in a lecture when I was in, I think, my 4th year in studying mathematics. And it took several weeks in my memory, and it's very complicated. There are different ways of approaching the proof, different techniques. And here are 2 references. There are many more, so that you may have other favorite references for the proof. But so this is where you can find them. Yeah, so a few quick comments and also discussion of if we have other terminal conditions or other constraints. So this scalar adjoint is a constant and non-negative. If the final time is fixed, so not an optimization variable, then we get this again, like in Euler-Lagrange as an additional condition. If we have a fixed final time and a Meyer term is considered, then the terminal condition on lambda is the derivative of this Meyer term with respect to x. And for general terminal constraints, we can again show, like similar to Euler-Lagrange, that we get this kind of terminal constraints. And I'm not really consistent here. I think Lx also here should depend on Tf. So this Tf is missing. Okay. Yeah. So what about this extra adjoint lambda 0? Well, the Hamiltonian in the Euler-Lagrange, this is all what I already said, is this one. And the difference to the Pontryagin minimum principle is that we now have this lambda 0. So if we know that lambda 0 is not 0, so it could be 0 or positive. If we know that it's positive, we can always normalize it to 1. Because if we just multiply the right-hand side by 1 over lambda 0, we get it equal to 1, and nothing changes. All the conditions are still satisfied. And then actually both Hamiltonians coincide. If we don't have state constraints, it is known that this is always possible. That's of course only a sufficient condition. If state constraints are there, this may still be possible, but then it gets much more difficult to find out whether it is, right? So, and optimal control problems where this additional multiplier vanishes, they are called abnormal, and they are really difficult to solve there. Then you have yes.
Sorry. Normally, you have also condition that the 0 lambda cannot be used.
Yeah, that's what we already had here. I guess it was briefly, maybe too quick. So this lambda tilde consists of both, and this cannot be identically 0. So that's what we have. Yeah, this lambda tilde is the pair. So wait, that's the lambda tilde is the pair. Yeah, that's the pair. Yeah, sorry, I was too quickly. Yeah. Okay. Yeah. So. Yeah, that was that. And then, yeah, let's us quickly compare to the Euler-Lagrange equations. As I said, so if this is the Hamiltonian, so this is the condition in the Euler-Lagrange equation that the derivative of the Hamiltonian with respect to u vanishes for each t. And the condition in the Pontryagin minimum principle is this here. However, what this means is that the optimal values here, they minimize this, and I think this star, no, so yeah, this is okay, that they minimize this expression. But this also means if they are minimizer, then, and if there are no constraints, like in the Euler-Lagrange equations, then there must also be local minimizer in the classical sense, because there is no boundary of the set of control values. And this means that the derivative of h with respect to u should vanish here for each point. And then we actually get this as a necessary optimality condition, that the derivative vanishes. And then you see that we have exactly the same condition. And if we then normalize lambda 0 to 1, we actually get the same equations as in the Euler-Lagrange equation. So in other cases, this Pontryagin minimum principle generalizes the Euler-Lagrange equations. They are contained as a special case in these equations. Okay, yeah. Maybe many of you are more used to Pontryagin maximum principle, and I think this is just due to the case that the principle was originally developed for maximization problems. Since I'm always minimizing here in my course, and we get a minimum principle, but it's just a change of sign, essentially, that makes the difference. Okay, here's the same example again. So now the only difference is that this u, which is this is actually not the right u. It should be this u with the double bar here. That this u is now a constrained interval, so we are not allowed to use any value of u. And what you see is that, well, nothing changes here. I mean, I have already reduced it here to the single variables. What changes here is that we have, instead of this simple equation which says that lambda is equal to u star, we have now this equation here, and then of course this terminal conditions. And again, by this you can essentially compute the solution. And what will happen is that eventually you cut off values which are too small or too large here in this interval to get that. So, okay. Now, I said yesterday that very often, and we will see examples, several examples tomorrow in the last part, where I will also have some more really real-world examples, where we would actually like to have an infinite horizon problem. And the question is now, can we simply set Tf to infinity here in the Pontryagin principle? Yeah, this is a simple example, a well-known example, which shows that this is not so easy. And the reason is that in order to get a full set of equations that we can really solve for, we need not only the equations that we have in the that we saw before with the Hamiltonian, so with respect to x, to lambda, to u, and these differential equations and this minimum or stationarity conditions. We also need this terminal condition for lambda, right? So lambda of TF must be something. That's the usual condition, unless you fix the terminal state, which we do not do here, right? So x of 0. So let's first have a look at what is the optimal control here. For this simple example, you can essentially compute it by a little bit of computation. So the optimal control, if you check this optimization criterion, if you check that, is simply minus the terminal state, which can be written in this form, right? You can solve this equation well, exactly by separation of variables and then come up with a formula after some manipulations. And if you want to minimize that, you see, well, if you minimize that, you have to minimize that expression, which means that you have to maximize the integrand here, right? And maximizing the integrand, if u is allowed to be between 0 and 1, is of course achieved when u gets as large as possible, so-called u constant to 1. This would be the optimal control. So very easy to see. And this is true for any horizon, be it finite or infinite, right? That's always, so there's only just one solution for the optimal control, and this is b constant to 1, and this would be the optimal solution then, and you see it's nicely bounded, so nothing explodes from 0 to infinity, because as t tends to infinity, this guy here goes to 0, so it converges to 1. Yeah, we have no terminal constraint, neither explicit nor implicit, which means that the terminal condition for the adjoint is just 0, right? This is what we had in the Euler-Lagrange equation and also in the minimum principle, and this is true for if TF is finite. And now the conjecture would be, okay, if that's the terminal condition for the adjoint, then the terminal condition, if we have like TF equal infinity, so an infinite horizon, should be maybe something like that, right? That would be the natural guess. So if you would ask me, how does this extend or must be modified if we send TF to infinity, should be probably that, right? So that sounds reasonable. But it turns out that if we write down the Hamiltonian and solve for the equations of the minimum principle, then we get, if we plug in the optimal control, which we already know, then we get this equation for the optimal adjoint, for the lambda star. And now we have the degree of freedom, which is the lambda naught, and this is unfortunately a bad notation because this is the initial, this is lambda star of 0 here. Sorry, this is lambda naught. Sorry, lambda of 0 is here. No, it's okay. This is the lambda naught. This is lambda of 0. And then what we do is we look at this expression, which is known to be constant, which is lambda 0 minus, so this is lambda of 0 minus the lambda 0 term. And now we check, how do we have to choose lambda of 0, right? This is a free parameter here. And if the horizon were finite, we would choose it in such a way that lambda star of TF would be 0. And in infinite horizon, what we see is, well, we have to make sure that the Hamiltonian here is minimized by u equal to 1. So whereas the Hamiltonian up here, right? So we have to make sure that here we know that the x is always less than 1 for the solution. We have to make sure that something negative appears here, right? So we need that this, sorry, negative, is that true? 1 minus x, sorry, oh, wait a second. We want h to be minimized by 1. Yeah, so we need a negative. Wait a second. This must be less or equal to 0. There's a sign error in there. Okay, let me see how this moves on. This is probably wrong, but it doesn't really matter because no matter how we choose, if we choose them equal and if we choose them non-equal, we always end up with a terminal condition which is not 0. right? So that's the important thing. There may be something wrong with the precise computation, but it means that this what we think, or what one might think is the right terminal condition at infinity is not the right terminal condition here. Just have to check where the sign error occurred. So x is less than 1, right? So this is positive. To make 1 the minimizer, we need that to be negative. So it's not the wrong sign somehow. Anyone see it immediately? Okay. Yeah. This one here. Yeah, it's usually either 0 or 1. Yeah. Okay, then if that is 0, but I mean, no, we have no state constraints here. So it should be non-zero, the lambda naught. Lambda naught should be non-zero because we have no state constraints. And then it must be positive. So we could actually set it to 1 if we normalize. That should be okay. Okay, let me check that again, and maybe I will put up a correction. There's something is not quite right with this minimization argument there.
Sorry, in the definition of example,
yes,
because we can minimize in the line 1 minus x times.
Yeah. Minimizing minus. Okay, that's a good question. Yeah, no, that's this one. It's minus. This is the minus. Yeah, no, the minus is there. That's okay. That's okay. No, I will check. I guess I won't be able to repair this online. I mean, what would happen if we turn this around, if we make it less or equal 0? Then we get minus infinity here, which is still, I mean, just the sign changes. So here we get probably, here we still get lambda 0, and here we get minus infinity. So still the terminal condition that you would expect that if you extrapolate from the finite horizon case doesn't occur. So I guess it's okay even if there is a sign error in there. Doesn't really change. Yeah, bottom line. What is, so the general structure of the minimum principle remains intact, so you can still use it, but it's hard to say what is the right boundary or transversality condition for the adjoint. And this was pointed out in 1974 in this paper. There is recently, so someone was able, actually my co-author who did some of these slides, Tim Faulwasser, he was able to come up with a solution that solved this for some optimal control problems, not for all of them. So he was able to identify certain properties that allow to define this the boundary condition at infinity. But this is beyond the scope of this course to explain. But if anyone is interested, I can give you more details. Yeah, I already said yesterday that the Hamiltonian I defined has some similarities with the Hamilton-Jacobi-Bellman equation. And if we look at this a bit more closely, this is the Hamilton-Jacobi-Bellman equation with finite horizon for undiscounted problems. And what we have here is, you see, you have the derivative of the value function times the vector field plus the cost. And the Hamiltonian that we defined is here the adjoint variable times the vector field plus the cost with lambda 0. And if we again normalize lambda 0 to 1, if this is possible, we see that if both equations hold, then we must have the identity that this derivative equals to that adjoint variable, because otherwise one of the two must be wrong. So this means that the adjoint is nothing but the derivative of the optimal value. At least if everything is differentiable. In the non-smooth case, it gets a bit more complicated. So there's really a very, very intimate relation between these two principles. Okay. Yeah, very quickly, if we have state constraints, and you can even make it as general as using this mixed input state constraints where you have some function g depending on x and u that should be less or equal 0 if you define it in that way. Then we can extend this. If you have that, you will have to use additional adjoints, which we call nu, which kind of multiply with this condition here. And then you have this problem with active, inactive constraints. If any one of you has seen nonlinear optimization with inequality constraints, all the difficulties that you have there then essentially also appear here, and it can be very difficult to handle. And of course, a natural question is whether here we also have a discrete time counterpart. And yes, there are. They may have some value for infinite horizon problems. For finite horizon problems, it's actually usually easier to use just the KKT conditions that you know from static optimization. That will give you usually more information and something which is easier to use. Okay, now I didn't spoil my quiz. So here we have our first quiz for today. I made the point that when we pass from Euler-Lagrange to the Pontryagin minimum principle, that we can use measurable functions, so L infinity log functions. And my question to you is, why is it important that the minimum principle works for L infinity log functions? And I have three answers that you can give. So first is, well, there are examples where such functions are really needed. The second is, well, it simplifies the proof. Well, more general functions make an easier proof. And the third answer is, actually, it's not really important, but it's just the way how the authors wrote it, right? So they decided to do that, but there's no real need for that. So please take your mobile phones, scan the code, and give an answer. It's nothing about right or wrong, right? So it's completely anonymous, and you can just, I'll give you 1 minute to think about, maybe also talk to your neighbor what they think, and then you can reply. Okay. Anyone need more time to think about the answer? No? Then let me see what we got. Okay, yeah. So 83%. I'm not showing this on the Zoom. That's switching is. I'm just telling it here. So 86. There is more. 86%. 88. It's getting even more. Say that, yeah, there are examples where such functions are needed. And yes, you're absolutely right, because otherwise no one would have done the effort. Let me show such an example to you. This is a somewhat similar. It's actually the same differential equation as this car I had yesterday. So the car that you can move on a rail or on a one-dimensional road, left and right. X is a two-dimensional vector consisting of the x1 is the position, x2 is the velocity, u is the acceleration. And here we have the constraint that u should not exceed -1,1. So we have a bound on the acceleration, very natural. We start at x0. We want to minimize here the quadratic cost of x1, so the position. So in order to minimize that, certainly the car has to be driven to the position 0, right? And eventually it should also stay at the position 0, because if it keeps on moving, it will create cost, right? Whenever it deviates from 0, it creates cost. So, and it's easily seen that, well, if you look at this a little bit and know a little bit about the theory, there's always a control that brings you to 0. The question is just, which is the cheapest way in the sense of this functional to get to 0? right? Starting from x0. And the solutions, they look like that. They are a bit small, I'm afraid. So this is the x1 component, so the position, and this is the velocity. And what you see here is that, interestingly, if we start here at 2, we first move away a little bit, but then we go down, then we overshoot a little bit, and then there's a certain point somewhere here. And from this point on, we are really exactly at 0. So the optimal solution drives the system exactly at 0, exactly to 0. But what happens in between, this is really interesting, is that we have switches here, right? So the control always switches between +1 and -1, right? So between the extremos here. So we have, and you see this in the velocity here, right? Because this is maximal deceleration, maximal acceleration, maximal deceleration. There's another maximal acceleration, and if you zoomed in here, you would see that this actually goes on infinitely often, but on shorter and shorter intervals. So it's really a control that jumps between -1 and 1 and shorter intervals, has an accumulation point for all the jumps, and afterwards is constantly equal to 0. So this is really an optimal control where you need infinitely many jumps, infinitely many points of discontinuity. Of course, this is still a special measurable function, but at least it shows that something like piecewise continuous with finitely many jumps, which is what many people use because it simplifies some proofs, is not sufficient for all optimal control problems. And what I find in particular interesting is that, so these are, infinitely many switches, that this is a totally easy problem, right? There's nothing, it's really a two-dimensional differential equation, linear, quadratic, functional. Very easy problems can really admit very complicated solutions. That's the complicated in the sense of not a simple function that has like a couple of discontinuities, but in fact an accumulation point of discontinuities. So yeah, I think I like this example a lot, even though the practical impact is of course somewhat limited, but theoretically a very nice example. Okay, yeah, let me summarize and let me bring up a point which maybe yesterday was not as emphasized. I tried to, but maybe let me emphasize it again. So all of the solution concepts that we had, the dynamic programming and the Pontryagin minimum principle, and also the Euler-Lagrange as the intermediate step, they had optimality conditions for the values of the optimal control U star that are pointwise in time. So what we had were really independent conditions on U star of t for each t, so conditions that you can actually evaluate independently. And that's a really strong result in all cases, because actually you're looking for some, so in the optimal control, usually things depend on each other. If you have a car and you accelerate a bit more at the beginning, you have to decelerate more in the end, right? So everything is connected over time, but still we get conditions which are really independent for each time. So at time 5, at time 6, at time 5.5, or in between, you always have conditions that you can evaluate independently. So that's really something that the people in the 1950s were able to achieve. But of course, you pay a price, right? You need auxiliary quantities, right? So first thing, let me first go to this here. So the difference dynamic programming gives actually necessary and sufficient conditions for optimal solutions, and we can actually do open loop and closed loop, so we can get feedback. So red is always what distinguishes them, while the minimum principle gives only necessary conditions and only works for open loop controls. Yeah, and this is what I said. So the conditions rely on auxiliary quantities. So you need to do something before you can do this pointwise evaluation of U star. Dynamic programming, you need to somehow compute or at least approximate the optimal value function. And this is characterized by either a partial differential equation in continuous time or by something which is quite similar, a discrete time, what I would call functional equation, the Spellman equation in discrete time. And in the Pontryagin maximum principle, you need the optimal adjoint, which is characterized by an ordinary differential or difference equation, more precisely by a boundary controlled problem. So you have a condition at the end also, not only at the beginning of the time interval, but also at the end of the time. And what is something I would like to stress, and I will stress this even more in the next part of this course, that in high dimension, finding this lambda star is usually much easier than finding V. Why is that? Because lambda star is always a function in one dimension mapping to Rn. So if n becomes larger, then only the image phase of this lambda gets larger. It's always a function of t. It's never a function of something higher dimensional. While the optimal value function, if we enlarge the state space, the dimension of the state space, then the domain of definition gets larger and larger. And this creates a much more difficult problem. You will see that why this is the case in the end. So essentially, the effort of representing lambda star, n-dimensional function of a one-dimensional argument, grows linearly in n. While representing an optimal value function V in some function space grows exponentially in the dimension n. So it's really much bigger. But this will really be in the next part. I will really state this much more clearly why this is the case and how this is the case. Okay, yeah, that brings me to the next part, and I'm wondering maybe it's easier if we have the 10 minutes break now, because this is much nicer, and then I do 5 minutes longer in the second part, because otherwise I would now start and introduce first things, and then we stop after that. So let's have the 10-minute break now, and we continue then with the numerical solution methods afterwards. Yeah, numerical solution methods. I showed you some simple examples where you can derive the optimal solution, but for most practically examples, this will not be possible. Hear me on the recording. So that means that in practice, you will really need numerical techniques that somehow compute not exact, but close, well, nearly optimal controls and solutions. Yeah, and the purpose of this part is that I would like to introduce some of these numerical methods for solving optimal control problems. And I would in particular like to compare methods that compute optimal feedback laws. And I would like to emphasize again, this is what you would usually like to have in practice, with methods that compute optimal open loop controls and trajectories, and also discuss the numerical effort of these methods a little bit, and show you methods that may be better in mitigating this numerical effort. Yeah, I've split this part in two main sections with two subsections. So the first will be methods based on dynamic programming, which compute feedback laws. And this will be, well, I will start with classical methods for Hamilton-Jacobi-Bellman equations. So classical really means classical numerical techniques borrowed from PDE numerics. And then I will introduce something which has become very popular in the last couple of years, deep reinforcement learning, where we use deep neural networks for the approximation of certain quantities that I will explain then. And then in the second part, I will talk about methods that compute open loop optimal controls. And I will start with methods that are based on the maximum or minimum principle. And then also turn to some methods which have become very popular for a good reason, called direct solution methods. They do not really require a lot of mathematical theory. That's why mathematicians don't really like them. But even I, as a mathematician, have to admit they work really well and are really efficient. So there is a reason why they are considered. And I will come to that. Probably I will probably get to the maximum principle until today, and then the direct solution methods will be Friday, the first topic then, before we turn to the real new things. Okay, let's start with methods based on dynamic programming. As I said, appealing because you can get optimal feedback laws. And for brevity, I will only look at infinite horizon problems here. That's actually a big advantage of dynamic programming, that it really easily applies to infinite horizon problem. That's quite a difference to, say, Pontryagin minimum principle and also these direct methods that I will discuss. They are not easily extended to infinite horizon problems. Okay, the optimal feedback laws, they are characterized by this relation or that relation. This is in discrete time, this is in continuous time. So we have to find values f of x that minimize this expression for a given x, right? And this will be the feedback, or this is this pointwise condition. And here we look at this derivative here. There are all these difficulties I already discussed, that it may not be regular enough to plug it into a differential equation. But anyway, in principle, this is what we want to do. And that's a rather easy task, and I will not talk much about this part of the problem. So what I will look at now, I will look at numerical methods for calculating v or some other quantity which is quite similar to v. Because once we have v, we can use f as the minimizer of the above expressions and are essentially done, right? So the difficult part is to compute v so that we can form this expression here, for example, that we want to minimize. And I will start with the continuous time case where I use this Hamilton-Jacobi-Bellman equation, so to the setting down here. So it's a partial differential equation. So the natural idea is, well, let's use one of the many methods that we have for partial differential equations, like finite differences, finite elements, finite volumes, and even more. And indeed, if you look at Google Scholar, you will find, if you Google finite differences, Hamilton-Jacobi-Bellman equations, you will get tons of papers, and same for all the other methods. If you know about these kind of methods, you probably know how to apply them. If you don't know it, I will not really talk about, because I would like to talk about my favorite method for solving Hamilton-Jacobi equations numerically, which is the so-called semi-Lagrangian discretization. And this book from about 10 years ago really contains many things of what you need to know if you want to apply them. And these methods are really tailored to Hamilton-Jacobi-Bellman equations, and they have some really, really good features that I would like to explain to you. First is a numerical property. It's called this unconditional stability. So if you have ever worked with finite differences for equations that depend on space and time, then you know that you have to have some relation between space-time step and space step and time step, because otherwise, if they don't have the right relation to each other, you can get instability. So instead of computing something that goes like that, you will end up with something that makes wide oscillations and so on. Here, there's no problem at all. These semi-Lagrangian schemes, they are really stable for all combinations of discretization parameters, which is a real numerical benefit of these schemes. But what is, in my opinion, even more important is that if you compute the feedback law from the approximation to V, you would also like to have an error estimate there, right? What you would like to have is you would like to say, okay, the feedback law I'm computing is, say, at most 10% worse than the optimal feedback law. And with these kind of schemes, you can do that. I will also explain a little bit at least why this is possible. And with all the other schemes, it's really, really difficult. So if you do a finite difference approximation and then get the optimal feedback from that, you usually can never be really sure how good that feedback is. It might be quite okay in practice, but you don't have theoretical estimates. So this is the important thing. Okay. That's the Hamilton-Jacobi-Bellman equation for the infinite horizon discounted problem with this discount rate delta here. And in the semi-Lagrangian discretization, you do 2 discretization steps. And the thing is, you do it first in time and then in space. And yeah, this is a equation. Do you see any t in there? No, there is no t in there. It's the infinite horizon problem, so there is no t dependence. But implicitly, there is some time, right? Because this expression that we have here, dv times f, this can be seen as a directional derivative, and it's a directional derivative along a solution. So you can represent this as a approximate this by a difference quotient. And this is precisely what's happening here. So we approximate this term, and due to the chain rule, we also have to incorporate that. We can approximate this by this difference quotient, where this x tilde u is a numerical approximation of the true solution. So in the simplest case, you take the Euler approximation. So x tilde u is just x plus hf x and u, and plug this in there. This is what you can do. And this will always give you an approximation of that term. And because you have this e to the minus delta h here and do the chain rule, you get this minus delta v of x on top. That's where it comes from. Yeah, and then you take this term here and plug this in instead of these first 2 terms here. You rearrange everything a little bit, and then you obtain what is called the semi-discretized equation. And what happens now is, well, you don't have any derivative anymore, right? So the derivative has vanished. What you have is basically a functional equation. And if you look at this a little closer, it's actually nothing but the Bellman equation. So what I have done here is simply what I explained yesterday when I derived the Hamilton-Jacobi-Bellman equation. I invite you to go back and look at these slides. I have essentially reversed a part of the derivation I have done before. With one decisive difference, I have plugged in here a numerical solution, and I have not touched the L here, right? So this L came from an integral. This I have not touched. This is just here, and the h just comes from the fact that I multiply with this h here. Right? So, but you can actually see this as a very crude approximation to the integral from 0 to h along the solution of L, if you like. But okay, good. Yeah, so this is now the equation, and step 2 is now the spatial discretization. So we still have an equation that is, oh, I have a typo here. This should all be x's, so not x naught, but x. So but these x's still come from well, essentially all Rn. So the first thing we have to do is we have to choose a compact set where to solve it, because we can't solve on an unbounded domain. And then we choose some finite dimensional function space, which you could construct by finite elements. For example, a very simple choice would be like continuous and piecewise linear functions, and you can always define them on simplistic grids in arbitrary dimension. You could also do piecewise bilinear functions, and you could use rectangular grids. I have played with that too. That's also quite convenient. And K would be our space step size. And let me maybe make a little sketch in just one dimension. So in one dimension, what we do is we look at functions. So here we have x now. The grid would just be these one-dimensional points, and then the set of continuous and piecewise linear function in one dimension would be functions that are defined by the values in these nodes here. And in between, we just interpolate linearly. So it's these piecewise linear functions of this form, right? And this you can conceptually do in any dimension. It just gets more complicated with the bookkeeping and everything. And these functions will always be determined uniquely by the values in the nodes of the discretization. So that's how you do it. Okay, that's the simplest way. You can do much more complicated things. You can do splines. You can do higher order approximations of other forms. So that's all possible, but that's not really the point. I would like to explain the concept. So that's this finite dimensional function space, and K in this case would be the maximal distance between two nodes here. Okay, and then what you can do is you can project arbitrary bounded functions from C to R to Fk. So essentially what you do is, let me draw another picture. You take an arbitrary function. Is there a colored piece of chalk here? No. And I will do it all with white. So you can take an arbitrary function. Let's make a continuous one just to have something nice to draw. And then what you do is you look at the values at these nodes of the discretization here. And then you interpolate linearly. And then the map from this arbitrary continuous function to this piecewise linear function would be this projection here, the pi k, right? It projects one function to another function. And it's a projection because if I would apply it again to the piecewise linear function, nothing would change anymore because we have already a piecewise linear function. Okay, and then what we do is we look at this equation and try to solve it in this space Fk. And how do we do that? Well, if we have a function from Fk, which is called now VHK because it has these two discretization parameters, then the left-hand side will, of course, be in Fk. But the right-hand side here, this may not be in Fk. So what we do is we take the right-hand side and project it back. And then we get an equation that can be solved. This should be solved for all, should be true for all x in C. Yeah, quick word on constraints. Control input constraints are really easy to implement. You just put them here, right, when computing this infimum. State constraints may be much more complicated. They lead to boundary conditions that may really complicate the computation. It really depends on how they are defined. That's not so easy. This is why state constraints are, well, often put in this soft form, right? Putting them into the cost function rather than really implementing them as boundary conditions. Okay, let me show you a little example. This is an economic example of this Viennese school of optimal control in economy, Gustav Feichtinger and others. This is an example where it's about optimal investment in a firm, and we have two variables here. X1 is the invested capital, X2 is the current investment, and U is the change of investment, right? So what you do is you really look at, well, a change of investment. If you are at the stock exchange and want to buy like more shares from whatever company, that's easy, right? But if you are really dealing with a true plant, right, with a company that produces something, then any change of investment will create costs, right? Because you have to, if you want to build a second plant, for example, to produce something, you will have many costs of enlarging. Also reducing creates cost. And this is reflected here, right? So the cost that we want to, well, actually we want to maximize L. So what we want to do is we want to minimize minus L. This would be, sorry, no, L is the yield. No, minus L is the yield. L is what we want to minimize. So this would be the yield. This would be, well, a simple term that says how much you can get back from investment, from the invested capital. This is a term that actually these two together, they define it. And what is important is that this, of course, here, the investment goes in negatively because you have to subtract it, but that the change of investment also gives you some negative cost. Whenever you change your investment, you have to pay. Yeah, and that can be very nicely solved with the problem with this solution method, precisely with this piecewise linear functions here. Actually, I use piecewise bilinear here. What you can see is that the optimal value function on this domain here from 0 to 6 and 0 to 1.6, this is x1, this is x2. It really has a line of non-differentiability. And you see it even better if you plot the optimal feedback law that you compute from that. This is this one. This has a discontinuity. So this is a typical behavior for these kind of models. They were actually somehow designed to have this behavior. Because essentially what you have is you have here a distinction between two regimes. here you have a small company, and if the company is small, you will never increase it beyond that level. If you have a large company, then you will never decrease your investment beyond that level, because this would simply cause too much change of investment costs. So this is what's happening here. And this was not computed with a fixed grid, but this was something that I developed a couple of years ago, where we used adaptive discretization. And this adaptive discretization puts more grid points when needed, and particularly these lines where we have this discontinuity, or here this non-differentiability, they are really, a lot of points are put there because the scheme determines that something is difficult there and that we have to provide a high resolution at these points. Yeah, so yeah, that works nicely. And actually there is something in between that I have already mentioned, but now I would like to make it explicit. This semi-discrete Hamilton-Jacobi-Bellman equation that we get after one step of discretization is actually nothing but the Bellman equation. So if we simplify notation, instead of VH, we write HV again. Instead of HL, we write L. Instead of e to the minus delta H, we write beta. And instead of this numerical solution, we just write G. Then what we end up with is exactly that, right? So this semi-Lagrangian discretization really first converts the Hamilton-Jacobi-Bellman equation into a Bellman equation, and then tries to solve that with traditional, like this approximation techniques. And this has several implications. So first of all, the feedback that you get from VHK, that can be seen as an approximately optimal feedback for the exact time discretized for the sampled problem that I explained yesterday. And this is precisely the reason why we can give error estimates, because we can really interpret what we get from this approximation as something that is valid for the discrete time problem, and via this mechanism we can do error estimates, right? So, and this also avoids the technical difficulties in continuous time, because we can really apply what we get numerically as a feedback that does not change continuously, but changes only in small pieces. And this parameter H precisely tells you what is the distance between two time points where we change the feedback law. Right, yeah, as I said, this also leads to rigorous error estimates, but there are two other interesting things. So first of all, the method that I described in step 2, this projection approximation, this can be applied to any discrete time problem, because we can apply it directly to that equation. But we can also turn this around. Any method for discrete time problems can be used in place of this traditional approximation in step 2, right? And that's precisely what I will exploit in a few slides. Let me, in between, quickly tell you, well, how do we solve this equation? And there is something wrong. Okay, I forgot. Sorry, I forgot the projection operator here. So this pk should be here, and it should also be VHK. So I somehow switched notation here, and maybe because I wanted to go for the Bellman equation. Yeah, right. Sorry. So we have removed the indices here. So, but it's this VHK, right? So, yeah. First of all, I mean, this is something that we have to check or to solve for all x in C, which is again still an uncountable set, right? C is a compact subset of the reals. But since Fk is finite dimensional, it's actually usually sufficient to check the equation for x from a finite set. And this is precisely what I said here. Such a piecewise linear function, for example, is determined uniquely by these values in the nodes. So we only have to make sure that the equation holds for the values in the nodes at these node points here, at these, and this is enough. If it's valid there, it will be automatically valid there in all other x because of this linear, piecewise linear structure, right? The projection operator must be here, right? That's missing, unfortunately. And then you see that. And so what is the usual way to do it? Well, you can simply do it iteratively. So this is a fixed point equation, right? We have a v on the left and a v on the right. And the usual easy way to solve fixed point equations, the first attempt would always be to iterate, right? You start with some v0, some initial guess, then you compute some, then you have some VI, and from VI you compute VI plus 1 just by using this 6-point equation as an iteration, right? So always I on the left, I plus 1 on the, sorry, I on the right, I plus 1 on the left. So you turn your fixed point equation into an iteration. That's the value iteration, and there are known conditions under which this converges. So there are many theorems that telling you under these and that condition you will really converge. So for example, if L is bounded and beta is strictly less than 1 in a discounted problem, this is a contraction in an infinity sense, and this will converge. There is a more involved technique, which is called policy iteration. So what you do is, again, you have some initial guess, and then you have already some VI. And then what you do is you look at the feedback law that minimizes this VI pointwise now in this set of points that are of interest. And then what you do is you solve the fixed point equation, but not with this infimum here, but for this fixed feedback law. And that's a much simpler problem. That's a linear problem. You can use like linear equation solution techniques for that, very efficient ones, like, I don't know, whatever you like conjugate gradient or these kind of things that they work very nicely there. And yeah, what is known is that under suitable conditions, value iteration typically converges linearly, because usually there's some Banach fixed point argument behind that, while policy iteration is a bit like a Newton method, it converges locally quadratically. But of course, each step in this policy iteration takes much more time. Okay, yeah, so this is how you would do the computation, what you would implement. There is a variant of that is particularly in the realm of learning used very much, and this is what is called Q-learning. And the main motivation, or one of the main motivations for Q-learning is that you may not always have a closed expression for this G, right? For the map that tells you how to get from one state after one time step to the next state, right? For example, we may only be able to make experiments, or we have like a simulation software that tells us what's happening, but no formula, right? So it's maybe really only very costly to evaluate that, and there may not be a formula that you can use. And then what is usually done, instead of computing the optimal value function, you compute this so-called Q function. And if you, let me go back one step, if you look at this equation, it's precisely the term that is in this infimum here, right? This is what the Q function is, right? So you compute the Q function instead of V of x. At the first glance, you could say, well, this is not a good idea because this depends on two variables, so it's more difficult to compute, more difficult to approximate. But it has some advantages, and the main advantage is if you want to characterize the optimal feedback law. So this is the equation that we saw already before that characterizes the optimal feedback law. So it's the term that minimizes this expression here. And if you now plug in Q, you'll see that this is Q and this is Q. So if you use Q, if you know Q, then this equation simply changes to that. And that means you can now determine the optimal feedback law, and this should be an F star here, just by knowing Q. You don't need to know G. Here you need to know G. If you want to infimize this expression, you need some formula for G. Otherwise, you can't compute the minimum here or the minimizer. Here you can do this without having to know G, right? You can really do it with just knowing Q. That's the big advantage. And so that means that F star can be determined without knowing G. If you only have experiments for G or a big simulation software that computes the steps but no formula, this will still work. And the classical Q learning is essentially just value iteration adapted to Q. So again, you compute Qi plus 1 as the Q from as this expression up here, where you then put Q as the V. So this would be essentially the V again. But what you can now do is you can construct these values here experimentally. So you have to, of course, make sure that you always get these triples where the last point is G of the first, but you don't need a formula. You can do this by running a simulation or running experiments or so. Very often, if you continue with for the next index, you just use the xi plus, and you compute long trajectories and use the data from the trajectories and plug them in here and do this iteration. This is the classical Q-learning. Conceptually, it's a variant of the value iteration, but for a different object. And with a little bit of different flavor because it has this data-driven flavor here, but mathematically, there's nothing different behind. Okay, yeah, this brings me to deep reinforcement learning. And what is the reason? Why should we consider something else? Well, the reason is that what I just explained works nicely in 1, 2, 3, 4, maybe 5 dimension, maybe a little higher if you really work hard, but at a certain point it just ends. And this is what is called the curse of dimensionality. And this is not a new finding. The curse of dimensionality, the expression goes actually back to Richard Bellman, who had also invented the Bellman equation, or at least it was named after him. So he already realized that this is all conceptually and mathematically a beautiful theory, but it has problems if you want to use it numerically. And the reason is the following. And this is what I said before. The numerical effort usually grows exponentially with the space dimension n, if we want to solve the Bellman equation on some subset of Rn. And why exponential? Yeah, say, well, you usually would have this discretization steps then in each coordinate direction, right? So if you have like a one-dimensional problem, you just have this one line. And in a two-dimensional problem, you would have to use the discretization here in that direction, but also in that direction, right? But then, of course, it is not enough to have points only at the boundary of your set. You need to fill the whole set. So this means that if you have n equal to 2 and use 10 discretization steps in each direction, you get 100 discretization points. And now assume you add another dimension, right? You get another 10, but then you have to use this 100 points and put them up like to fill a cube, right? So you get 1,000. And this really goes up exponentially. So you have to, if n equal to 5, you have already 100,000. If n equal to 9, you have 1 billion. And this becomes computationally infeasible very quickly. And 10 discretization steps in each direction is not much. Only very simple problems would be approximated in a good way with that. Yeah, so I did stuff of these many years ago in my PhD thesis, and I managed to solve 5-dimensional problems, say, with okay accuracy. If you look at the literature today, well, there's quite some progress in hardware and software and anything. So people can nowadays get to 7 or 8 dimensions. And this, in my thesis, is 35 years ago. So this really means that in 35 years, and with all the progress in computer technology that we had, we were able to get from 5 to 9 dimensions. And this is not with high accuracy. So there is really a problem. These grid-based or mesh-based methods, they really don't work in high dimensions. So this is not a way to go if you want to solve high-dimensional problems. So Friday, I will have an industrial use case where I helped a little bit solving a problem. This is a 60-dimensional problem. So, and I will show you examples that we did theoretically on Friday, which go up to 200 dimensions. And still they work, but they don't work with grids. So they work with something else. And this is exactly what is this deep learning here. They work with deep neural networks. And I will provide a brief introduction now. So I assume that many of you have seen them before because they are everywhere, but to make sure that everyone is on the same page and has at least the same basic knowledge, I would like to introduce them quickly in a couple of slides. So we have a little excursion on neural networks, and I will start with a quiz. So I would like everyone to participate. If you know what a neural network is, very well. If you don't know, just guess what might be true. So the question is, which of the following mathematical objects does best describe the nature of a neural network? Would you say it's something like a matrix, or maybe a function, or maybe a sequence, or maybe an equation? What do you think does best describe a neural network, what a neural network does? Give you 1 minute to answer, and then we check what the majority of you thinks. Anyone need more time? No, then let's have a look. Okay. 12 answers. Okay, so this is in German, unfortunately. 12 answers, and I think I would say that 4 of you say a function and 8 say a matrix, if I interpret the figures with a rounding error right. Well, matrix is not entirely wrong because there are parameters that you can arrange in a matrix, but this doesn't really capture the functionality. And those 4 of you who said a function are really closer to the truth, at least in the context that I have here. So this is the neural network structure that I have in mind that we will use. So what does the neural network do? Well, you have what is called an input layer. Here you just plug in values, and each circle here represents a scalar value. So this would be a 4-dimensional vector of values. And then something happens in between. So from these values, you compute a first hidden layer. From these values, you compute a second hidden layer. Then you compute a third hidden layer. There are also networks where you can skip layers, but I don't have that here. And then from the final layer, you compute something which is an output layer. And since everything depends on these 4 input values, essentially these output layers are just 3 scalar components of a function. So what we have is really, so neural network representing a function f of x. We have here the input vector and here the output vector. That is the map f of x. So it's really a function, and that's a good thing because this is precisely what we will need for reinforcement learning and for our applications of neural networks. Of course, there are many things. Neural networks can talk to you like a real person. If you think of ChatGPT and other generative networks, you have image recognition where they do amazing things, find out in your huge pile of pictures that you took with your mobile phone, all the images where your best friend is on or so whatever. So this is all possible, but we are thinking about functions, so this is a much more mathematical application and interpretation of neural networks. So here we get a function from R4 to R3, as everyone has seen. And the question is now, what happens when we move from layer to layer? How do we compute the next layer from the previous layer? Yeah, let's have a look. So we look at one of these layers here, this one here, and I would like to explain how this value here is determined. So first of all, it depends on everything which is there before in general. And it is just essentially a linear combination. So we have these weight terms, and they multiply the values on the previous layer. Then we have what is called this bias term here, this B11. And all this together comes into a function called sigma, a scalar function. And this gives us this value y12 up here. So we multiply each of these values here with a weight, the W things there. And then we plug the sum into, well, we add some constant, we plug the sum into a certain function sigma, and then we get this function out. Okay, yeah, so these are the weights here. They kind of multiply the values that get in there. And as I said, W are called weights, and this B is called the bias term. This is the short way of writing it, convenient with a sum. And this works for arbitrary L here. And L is always the level or the layer, actually. So this would be the second layer. This would be the first layer. And of course, if we are in the very first layer, then the input would not be y's, but the x's, right? Yeah, sigma is what is called an activation function. And there are many different choices. In classical neural network theory from the 1990s, you would very often see these called sigmoid functions. In modern applications, you very often see this ReLU, which is called rectified linear unit. I have no idea who came up with this crazy name. So linear unit means it's just a linear function, in this case, just the identity here. And rectified means that we cut it off here and extend it by just 0 to the left, right? And this is what this max thing does. For some reason, no one really bothers about the fact that we have a non-differentiability here, which in theory is kind of disturbing, but in practice, it doesn't seem to make a problem. So ReLU is really very popular, in particular because ReLU networks can be really evaluated very quickly because the function is so simple that you have to evaluate at that point, right? So that's really easy. Well, I usually bother about non-differentiability. So what we have done in some of our applications is to use the soft plus function, which is just a smooth approximation of the ReLU. And you can actually add another parameter that makes it more and more close to the ReLU. So but it smoothens out this kink that we have here. Yeah. Okay. In practice, of course, you would like to find, you somehow have to find the right weights and bias terms so that the network does what you want it to do. And the simplest task that you want is that you have a given function and you would like the network to approximate that function, right? That's the simplest way. So let's call phi d, d for desired, the function that we would like to represent by the network. And then we need some training algorithm. That's what it's called. It's essentially, it's iterative optimization. And for optimization, we need some objective, right? And the objective is what is called loss function in neural networks. And let's start with the notation here. So phi is the function represented by the neural networks. It depends on x and on theta. X is the input vector, and this theta or theta here are all parameters of the network. So all the w's and b's I put into this big vector theta here. Right, so that's what we do, and then x1 up to xn are the function arguments, and y1. These are vectors here, right? So these are really different arguments. This is the data that we use for learning, and then we know that we have function values. And what we want is we would like to have that for all arguments, our neural network matches as good as possible this function value yi, right? So yi is the value of the desired function in xi. And this term here simply penalizes the distance. Whenever phi does not coincide with yi, we get a positive term. If phi coincides, phi of xi coincides with yi, we get 0. So the minimum of this function is the function phi, which is in the least square sense closest to this function phi d here on the data set. That's what it does. Yeah, that's the standard loss function for regression or least squares. And in learning, you call this supervised learning. Supervised because you already know what the function is that you want to represent. So you kind of teach the network by showing them the values that you would like to have. Right? So learning a function with prescribed values at the data points. Yeah, how would you do that? So this is usually, so the usual method is gradient descent, although more and more also second order methods come up in deep learning, but gradient descent is still the most popular method. So what you do is you compute the gradient of that function with respect to theta and go one step in the opposite direction to make it smaller. And then you compute the gradient again, go again one step. So it's really a gradient method where you follow the gradient to a at least local minimum, hopefully a global minimum, right? So this is what it's done, right? So the parameter vector at iteration i+1 is the parameter vector before minus some learning rate or step size times the gradient with respect to theta that is of L, right? L of theta in theta I. Yeah, they are very efficient to implement because what you can do is you can really compute the derivative of a neural network with respect to the parameters theta, and this should be a phi here, right? So this phi, sorry, not an f. You can really compute this derivative very efficiently via something which is called backpropagation, which is nothing but an efficient evaluation of the chain rule along the neural network, right? You have all these layers, and if you want to compute derivatives, you have to use chain rule, and this is what is called backpropagation. So they have lots of new names for things that we know since ages in mathematics. The trouble is if we have huge data sets, so if we have lots of xi and yi here, and this is what we usually have in deep learning, then this computation of this gradient involves a huge sum. And this can take very long and can be very inefficient. And what people came up with is a really, really clever idea. In each gradient step, we only we pick randomly a subset of data points, much smaller than the overall amount of data points. And then we compute the derivative, this derivative here of L with respect to theta. we compute this only for this subset, right? So we only take a much smaller sum, define L with a much smaller sum, and compute the derivative, make one step, then we get a new set of data points randomly, we compute the next derivative, and this is much, much faster and not much slower in terms of convergence. This is what is called stochastic gradient descent. And I have a simple example here for you where you can see this, how this runs. This is learning a function. Takes a few seconds to set up everything internally. Yeah, that's the data I provided. So let's make this big. That's the data I provide. These are the xi's, these are the yi's, and I guess you can easily see what kind of function I would like to learn the neural network. So the xi's are chosen randomly, and the yi's I just evaluated the sine function, I think sine 2 pi of x, right? 2 pi times x. Okay, now if I close that window, then the computation will start. And now this stochastic gradient descent moves on here, down here. You see this is the loss function. And after it's finished, I can plot what the neural network does. So I just feed in the neural network, into the neural network, the different x values. And this orange line is what the neural network does. The blue line that you see a little bit here maybe is the true sine function. So you see that the learning is not perfect here on the edge, but all in all, even in the gaps between two data points where we had no information, it fills very nicely the sine function nicely and continuously. And that's actually a feature of neural networks that is interesting. So even if we have large gaps in between, it doesn't do something strange like going up and down. It tends to kind of smoothly fill in the gaps between the data points. Okay, yeah, so this is the sine function. And now let's go back to dynamic programming. So if we want to do deep learning for computing either the value function or this Q function that I introduced, then the idea is very simple. We use a deep neural network in order to represent this an approximation to this function. And I will call this now VNN or QNN. These are the approximations to V or Q, and they are represented by deep neural networks. Yeah, one possibility for choosing the loss function is the following. So yeah, we would like to minimize this squared, this squared term here, or for Q, it would be this squared term. What is it? Does anyone see immediately what we are minimizing here? Well, I can show you. It's the violation of the Bellman equation. So if the Bellman equation is satisfied in all the data points, then this expression would be 0, right? Because this is just the Bellman equation, put everything on one side. And if the Bellman equation for Q, which you get by just modifying a little bit, is satisfied, then this would be 0 in the data points. So this means that we can really, the simplest attempt would be we just use the residual of the Bellman equation as the loss function, the squared residual in that case, in the data points. Right? And data points are collected more or less randomly. Here we just need xj and just xj's. And here we need xj, uj, and this xj plus because of the structure of the Q learning. Yeah, if you try to implement that, it's not so easy. For simple problems, that works. For more complicated problems, it's hard. First of all, it's a very complicated term that the optimizer has to minimize. And then, yeah, that's. Yeah.
So you are now trying to approximate a neural network function some values.
Yeah. Yeah, they are not known. I'm not. That's the point. I'm not computing beforehand the value function. It's not supervised learning. It's reinforcement learning. I'm trying to find a function that satisfies the Bellman equation by minimizing the violation of the Bellman equation. So I don't, that's, okay, maybe I didn't make this precise. It's a different kind of learning. Supervised learning, then I know the values of the function. Here I don't. And that's why I use the Bellman equation as a proxy. And I mean, if the learning is successful, you would get exactly what you want. The trouble is that minimizing this with this gradient or stochastic gradient descent is really it's a hard task, right? And this is why, okay, before I go to that, this is what you would do in continuous time if you want to use the Hamilton-Jacobi-Bellman equations. Actually, derivatives of neural network functions are not that difficult to get, so that's feasible. But again, the optimizer will have a hard time. And one particular difficulty is that we have this infimum in there. But also the overall setting is a bit difficult. And that's why you somehow return to this value iteration idea, since the minimization is, and do some iterative things. So what you do is you again put some index here, some iteration index on your VNN, and you get some initial guess. And then from VNNI, you compute VNNI plus 1 by minimizing this loss function here. So actually, this, of course, you have to sum over the data points then again. Right? So this would be the loss function that you sum up. And the nice thing is that this is a standard regression problem. This is supervised learning in a way, because you would like to have this function to assume this value here. Right? So that's again supervised learning, but one after the other and iteratively. And then you have to analyze that. It's not easy to really prove that this will converge.
Excuse me.
Yeah.
The notation of slides here, what is phi and what is y? Y is the value.
So in the notation of the previous slide, what was L here would be one term here in the sum, right? There is no the phi would be the VNN. Yeah, VNN, and now I have like there is no y. Okay, yeah, sorry. This would be the phi, and this would be the y, because this is from the previous step. It doesn't change anymore, right? So it's from the previous iteration. And yeah, this can be a standard regression problem. Then another thing you could do is, or maybe let's stick to that, because this is already a method that works quite well, even though it's not really clear. And I would like to run a little learning. This is reinforcement learning code that learns the balancing of an inverted pendulum. And at the moment, it just produces random solutions and is learning, right? So it's learning the from iteration to iteration. And whenever it's more than a certain angle from the upright position, it starts again in the middle. So it produces a lot of solutions just by simulating, and feeds the neural network and does the iteration that I have shown you. We will come back to that in 2 or 3 minutes, and it should have learned something. Okay. Yeah, so as I said, the inf is another problem here. So in that implementation, the inf is there and it works okay. But in general, the inf is difficult because you have this inf inside a function that you want to optimize over. So it's like a nested optimization problem. And one typical way to overcome this is that you use another network, FNNI, which stores an approximate minimizer. So you first compute FNNI as an approximate minimizer to that term, and then use that here in place of U, right? And replace this infimum. This is what is called an actor-critic method. So F, the feedback would be the actor, and this loss function here would be the critic that tells us how good the feedback was, right? In a way. And yeah, once an approximation to F is taught, once we have introduced that, then we can actually also optimize directly and use the cost function as part of the loss function. This is a very recent development, couple of years old, called the policy gradient method. That seems to work also quite well. And we are currently having a student who is exploring all these kind of things. Yeah, data points. Yeah, question.
Since you are here, you use, for example, all points of your space, then the neural network would be perfectly equal to the vector, right?
Right.
So it means that how many parameters your neural network?
That's the point. So it will be, at least in theory, and if everything goes well with the training, it will be perfect if the neural network can represent the function that you would like to. So you need to, and then the question is how many parameters. This is all on Friday. So I will talk about this on Friday. I don't want to anticipate that here. So I will really talk about this in depth on Friday. This will be half of the Friday course on how this can be determined. But it's the important question. I absolutely agree. Okay, yeah, so what also happens is that data points are often generated along trajectories. This is like these short pieces of the pendulum you just saw in the simulation. They are called episodes. And very often what you do is you use generated data several times, not only one time, so you use it again and again because there is some iterative learning. And if you present the data again, well, this is something we all know, right? If you do an iteration based on Banach's 6-point theorem, we also use the same data again and again, and still we get improvement. It's the same here, right? You don't always need new data. You can do an iteration twice with the same data and still get progress. And if you do this iterative thing, this is what's happening in the back in this pendulum stabilization, then actually you don't do a new iteration after each data point, but actually you collect a certain episodes of new data, and then you do an update, because otherwise there would be, not much progress in each update. Let's have a look. What does it do? Where is the, there it is. Better already, right? So it has already learned something. And it's still training, but it's already using the feedback based on what it has learned already. So this is why the single episodes last much longer now, right? It takes much longer time before it actually falls down or reaches the boundary of the value. So it's already learning something. So this is what is written here. So the controls that used for generating the data are chosen as minimizers of the Q that we already have, or the current QI. And this would be the exploitation. But we have to randomly also generate exceptions, otherwise there may be controls we never see and never use, and they might be even better in training. And this little simulation, what you see, I got from this spinning up openai.com with some improvements. So it doesn't work that well if you get it directly from the website, but this is something you can check, websites you can check to get some code which you can play around with. And yeah, part 5 of this course, this is really about whether deep learning can do better and about the number of parameters. So I hope you bear with me until Friday, and then I will explain that. Okay, I think time-wise, this is a good time to stop. So this was all on what I wanted to say on numerical methods based on dynamic programming. We can watch the pendulum a little bit while it still trains balancing and already was. If we wait for another, I would say 2 or 3 more minutes, it would balance for a very long time. So, and yeah, tomorrow I will start then with the numerical methods that compute open loop optimal controls. No, not tomorrow, on Friday, sorry, Friday 9:30 as written there. And then I will come to the 2 advanced techniques that build on everything that I have told you so far. This will be model predictive control. This is a way to use open loop algorithms to create a feedback law. I will tell you how this works. So open loop algorithms are often much faster, so this is why they are good, but they don't give a feedback, so we have to do something to get a feedback. And the second will then be this analysis of deep neural learning. How large do we need the networks to be? Are there classes of problems that we can do with relatively small networks, and what does characterize them? Okay. Thanks for your attention. See you again on Friday.